Okay, so let's go ahead and get started. Any questions about anything before we get going here? So we were talking yesterday about how data is represented inside the computer, what it looks like laying in the memory of the computer. And we had talked about the idea that we like to deal with things in chunks that are 8 bits wide called bytes, and that the Intel computers are byte addressable computers. So as the addresses go up, they're pointing at successive bytes, 8-bit chunks in memory. And we noted that we like to write things down in hexadecimal because one hex digit represents 4 bits. And so to represent the contents of a byte, we can just write 2 hex digits down, and it's a lot more convenient than constantly trying to convert back and forth between binary and decimal. That would just be really a painful thing. So the example that we're looking at on the screen here is this assembly language instruction that has a that $ means that this is a constant. And then the OX is the same as in our C conventions, meaning this is a hexadecimal number. And so we have the number 1 to AB, and we're understanding now, hopefully, that this Intel computer is a little Indian computer. So the least significant byte, those 2 hex digits, is stored at the lower address, and the most significant byte, the 1 and 2, is stored at the higher address. So that's okay with everybody. So we have this little program that we can use to dump out the contents of memory. And I have this in an actual file out on Schofield that we can run. So this little function here called show bytes, there's a number of little C things that you have to learn in order to understand this little example. So we'll just go through them one at a time. The first thing you see here is a type def. So that's how you create user-defined types in C. You start off in C with the base types, which are these guys, right? The chars and the shorts and the ints and all those kind of guys. Those are the things that are built in the language, if you will, that come intrinsically in the language. But you can define your own types that are sort of built up out of all those base level things that are already there. In addition, you can have arrays and structs we'll talk about later, but this type def is defining a new type, and the name of the type we're defining is a pointer. That's the name we're giving to the type we're creating. And what we're saying a pointer is that splat means pointer. It's a pointer to a unsigned char, which sounds a little strange to say unsigned char as opposed to just char. You could have just said char and it would have been the same thing too. But what we're trying to express here is this type, when we create a variable of this type, it's intended to hold an address that points at a byte in memory. That's all that's trying to express, right? And so then we have our little show bytes function, and like all functions in C, the first thing you see is the return type coming out of the function. Like in main, it returns an integer. Well, this guy, show bytes, doesn't return anything. So the way you express that in C is you write void as the return type. Many languages have the word function and the word procedure that they use. And when you use function, that's something that you pass some parameters into and it returns something back. And the word procedure means, oh, you just pass a bunch of parameters in, but it doesn't return anything back. So C doesn't have those words function and procedure. So to get, the only thing it has is functions. And so to make it behave like a procedure that doesn't return anything, we use this little void thing, right? So our function name is show bytes, and then we have our parens and our parameters that we're passing into the procedure. In this case, two parameters. One has the name start and the other has the name length. The length is an integer, which is how we're going to indicate how many bytes you want to walk across in memory and show the contents of. And this start thing is one of these pointer types that we defined up here, right? So what start is what? It's an address that points at a byte sitting in memory. So we declare a local variable I, and now we have a for loop. And the way a for loop works in C is that you write the word for, and then you write a set of parentheses, and you have three things in your for loop. You have the initial thing you want to have happen, and then you have the test for whether you want to go through the body of the loop, and then you have what happens after you go through the body of the loop. So the typical thing to write a for loop that just counts, right, is you set a variable to 0. You'd see if the variable was less than the number of times you wanted to go through the loop, and then you'd increment the variable after you went through the loop. I plus plus is just a shorthand notation for I as assigned the value I plus 1, just a shorthand. So all for loops have these three things, and you can leave any or all of those out, as it turns out in C. Um, C thinks of everything as just sort of a template for what the compiler is going to spit out in the assembly language. And so you can use a for loop for an endless while if you want by just leaving everything out and putting two semicolons. So in other words, it doesn't have to count. It could be various things you use for loops for. But the normal sort of thing you want to do is you want to iterate across some range of values. And the canonical form would be to start at 0, and then while it's less than the number of times you want to go through the loop, and then increment. In early versions of C, you couldn't declare this variable I right here in the for loop. You'd have to do it like out here. In later versions of C, I think starting in C99 and later, I think it'll let you do that if you want. The for loop body is a single statement, in this case, this print statement. If we wanted to have a whole bunch of statements, we would have to do this, right? We put our little set braces there. And then this is now a compound statement. It's sort of like, okay, it is one statement, but it's a compound statement. And then you could put 47 statements in the middle there, right? But if you only have the one thing, you don't need the little brackets. So the way you have to think about that is for, and then you give it a statement, but the statement could be a compound statement, in which case, yeah, whatever. So the one statement we're doing here is this little printf function. And the way printf works is you always give printf, the first thing you give it is a string. The hello world program, we just put the literal string hello world new line in there, and that's all we wanted to do. But the normal sort of stuff you'll see in using printf, print formatted, is the string has embedded in it little format specifications that match up with this list of things that I'm going to print out. So the way you have a format specification in your string is you put a percent sign and then some magic incantation that tells it what the format is. And there's a whole bazillion of these that you'll learn. This particular one, percent %P, is just telling him that this thing that it matches up with, the first thing here, is an address, a pointer P, right? So it's saying you're going to print an address out. And then the second format specification, this guy here, this is putting a tab character in, right? Just like the new line /T. And this whole business here, all that junk there, is the second format specification that matches up with this guy, the second guy in the list. And it's saying, I want to print out literally the characters 0x, and then the format specification is this percent dot two thing, excuse me, which is telling him that I'm going to print this thing out in hexadecimal in two character positions, right? So that one mates up with that one. This one mates up with that one. And so that's the way you generally use printf. You have some bunch of stuff you want to literally print out, but then you have these little percent things in there that are the specifiers for the format that match the variables in the list. So what are these variables what are these things we're printing out? Well, start is what? It's one of these pointers that we created, which in turn is what? The address of a byte in memory. So we're printing out an address there, right? And we're doing arithmetic on that address, adding the loop variable to it. So whatever address you pass into this guy, that's the first address that gets printed out. And as it goes through the loop, incrementing the I, it just walks across memory to successive addresses, right? Prints those addresses out. And at each place, it prints the contents of what lives at that address. And so this is a little weird C thing that you'll get accustomed to eventually. In C, we try to take the concept of a pointer, an address, and sort of mush it together with the concept of an array. Here you see we're using this address that came in here as if it was an array. Well, that makes sense if you think about it. If you think of an array as specifying the start of the array where it lives in memory, and then the subscript just is used to compute down off of that start how far down you're going in memory to pick up the indexed element. So you can interchangeably in C use addresses. First off, you can do arithmetic on addresses, and you can use addresses just like they were arrays and subscript them. So this is going to print the address that you passed in and the contents of that address. It's going to print a byte, right? And then it's going to go to the next one and the next one and the next one for however long you told it to walk across memory, showing you the addresses and their contents. And then we get through, we print another printf. So any questions about our show bytes function? So now to test it, to actually do something with it, have a little main that calls the thing, right? You always have to have a main if you're going to actually run something, right? So he declares a variable a to be an integer, and he puts the decimal number of 15,213 in it. And then it just prints out this string. The int a is 15,213. And then it calls the show bytes function. And what does it pass it? We got to pass it two parameters. We got to pass it the address that we want to start at. So this ampersand, when you put ampersand in front of a variable name, it says, give me the address where this variable lives in memory. but we declared our parameter to be our pointer type that we created. So we have to cast that address, which is just a generic thing, right, as a pointer type, which is pointer to char. So this is how you do a typecast in C. You put parentheses around the name of the type you're casting it to, and you just butt it up against the thing you want it to operate on. Really horribly designed syntax, right? So it says, give me the address of the variable A, cast it as a pointer, hand it to this guy. And then this size of is a built-in pseudo function because it's not really a function that runs at execution time. It's something the compiler just knows. And it says you hand it a type and it says hands you back the number of bytes that that type takes up, which in the case of an int we know is 4, right? So that's going to pass it an address of this variable and 4, and then it's going to walk across memory for those 4 bytes, printing out the addresses and the contents of what's sitting at those addresses. Does everybody see what's going on? So this is Emacs, and so for those of you who came yesterday to the office hours, I'm going to compile the thing, right? So I'll do my Alt X, compile, and I've got my compile command already set to run the GCC compiler, put the output in test show bytes, and I want to compile test show bytes. So boom, I compile it, and it's saying, hey, you messed around with this file and modified it since you last saved it. Do you want me to save it before you do this compile? And I'll say, yeah, save it. So now I get the results of the compilation in this other little window here, and everything went fine. Here's the command that it ran. And I get my exit code 0 saying there weren't any errors or anything like that. So I'll come up to this window and do my Control X1 to just get back to the one window. And now I want to run the program that I created. Well, I don't have to go down to the shell and run it or whatever. I can do it right out of Emacs here. And the way you do that is you tell Emacs, I want to run a shell command by saying Alt exclamation point. And then you just type the shell command you want to run, which in our case is, oh, I want to run this little test show bytes executable I just made with the compilation there. And when I run it, I get this other little window popping up here that shows me the output of that shell command that I ran, right? Which is our program that we're playing with. So what does the output look like? Well, this printf here did A is 15, blah, 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 right? And then here in the loop, in the, oops, I can get it back. The loop in the thing, crap. Let's just do it again. The loop that's running here. So here's the address that gets printed out, and this 0x is, of course, our convention for saying this is a hexadecimal number. That is a result of the fact we use this little P format for the address, right? And then here's our tab character. Boom, there's the tab character, right? And then this is saying print 0x. Well, there's 0x. And then print the contents of the memory location as 2 hexadecimal. That's what the X means. 2 hexadecimal digits. Percent dot 2x is print that in 2 hex digits. And so that's where this is coming from. So it's walking across memory, printing the address we're at, and then it's printing the contents for the 4 bytes that are occupied by that integer variable, right? So can I look at that and tell whether this computer is a little Indian computer or a big Indian computer? How many think yes? Nobody thinks yes? Can this reveal to me whether this is a little Indian computer or not? Well, yeah, it can because I see at the low address, I've got the least significant part of that number, that decimal number. The upper parts are all zero, right? Because that's not big enough to require bleeding into these upper bytes. So I can look at that and say, oh, this is a little Indian computer that's got the lowest address, has the least significant byte. The ampersand A always means give me the address of this variable that it's sitting in front of, right? Just stick it in front of any variable and that gets the address of that variable. But when you get an address, that's sort of a generic thing, right? Address. And so we had to cast it to this type we had created called pointer here, right? We could have just not done all that pointer gibberish and creating a new type. And right here in the parameter, we could have just said char splat, and then we wouldn't need the cast or whatever. Okay. Oh, we'd have to cast it as a char splat down here too. So scratch that. So any questions about this little program that walks across memory starting at some location and shows you the contents of the memory? Okay, good enough. So it's just showing you in the slides, the same thing that I had in my main program, main function in my program, right? So if we had a Intel 32-bit computer and we had that decimal value, it would look like that sitting in memory, right? 4 bytes, right? If you were on the Sun Spark processor, which is a 32-bit big Indian computer, and you ran that program, it would come out looking like this because the least significant byte would be at the high address, right? If we had a long int, remember on 32-bit computer in C, a long int is kind of like a lie, right? You don't get anything bigger than an int. You still get 4 bytes. So if you were on the 32-bit computer and you declared that thing to be long, you still would only get 4 bytes, the same thing you get if you declared it to be an int. If you're on the 64-bit computer and you declared it to be a long int, you actually do get 8 bytes. So you'd get those things, and then you'd see 4 more bytes for where that variable lives. It takes up 8 bytes. The 32-bit Sun Spark processor would be the 4-byte thing in reverse order, right? Now, if we had negative 15213, that would be that encoding, right? We'll learn about a thing called two's complement encoding for integers, and we'll see why that is the encoding for negative 15213. So it would look like that. Covered later. So the pointers just depend on whether you got a 32-bit computer or a 64-bit computer. A pointer, if I declared a variable b and put negative 15213 in it, and then I declared a variable p, which is a pointer to an integer, and I put the address of the variable b in it, right? Does that make sense? Then I printed out what is in p, It's some address wherever the heck it ended up being in the computer, some arbitrary address, and it'd just be some 4 byte address in the 32-bit Spark processor, the 32-bit Intel, it'd be whatever address it is, and then the 64-bit, it'd be a 8 byte address would come out in the 64-bit computer, right? So that the effects of the little Indian, big Indian thing on how the integers are stored in the memory of the computer. How do we store strings in the computer? Well, we're writing in C anyway. So if we declared a array, which is how you declare an array, you put the little brackets and then how many things you want in the array. And all arrays in C are subscripted beginning with 0. So when you declare this thing to be 6 big, the subscripts you use on it are 0 through 5, not 6, right? So this says how big is it? 6 things. The subscripts are 0 to that minus 1, right? So we're declaring an array of 6 characters or 6 bytes of memory, and we put this string in it. Quotes means it's a string in C, right? And what are we putting in there? Well, the 5 characters that represent the symbol for 1, the symbol for 8, the symbol for 2. This is not an integer number like we did when we had an integer in the previous thing. This is a series of bytes that are using the encodings for those symbols, those printable symbols, right? And you'll see that it doesn't really matter whether the computer is little Indian or big Indian. Strings all look the same. It starts at the low address and puts this left one in there and then walks across and puts them in sequence. They're the same regardless of whether the computer's little Indian or big Indian for a string. But why is it 31, 38? Why is that the contents in hex of those bytes? Well, we'll look at the ASCII code chart and see why that is. Encodings that are used for all these printable symbols in the ASCII code chart. You see that gives it in decimal, hex, and octal, and whatever. So we're printing the number 1, right? The symbol for the digit 1 in hex is 31, which is why you saw 31 on the previous slide. And these things aren't arbitrary. They're arranged in a very logical sequence, right? The symbol for 0, 1, and the digits, they just get bigger one cross. The symbol for a capital A, 41 hex, and notice that the lowercase a is 61. It's 20 hex locate numbers bigger. So if I wanted to convert uppercase A to a lowercase a, I could add 20, treating that as a number, and I'd get the encoding for the lowercase a, right? All the ones up to 20, which is a space, are non-printable. And the last one here is non-printable. Everything else has got a printable glyph, a representation, although technically space, you could argue that, right? But all the ones up here to 1F, 31 decimal, are non-printable. That's where our things like line feed and tab character, all those kind of guys, that's where they live, right? They don't have a printable symbol. And so that's why we're using these conventions like /t \n to represent them in C, because they don't have anything that you can print for them. So questions about the ASCII character chart. So that's why the thing says 31 there. The value 31 sitting in a byte, right? You could interpret that as a number and use it as a number, but it really, in this context, is being used just as the encoding for the symbol one, and then 38 is for the eight. The other thing that's going on with this string is you'll notice that it has this 0 byte down at the end of it. And that's the way strings are stored in memory in C. We only put digits, five character positions in our string, our array here, right? So why did we declare it to hold six things? Because we had to leave room for the null terminator. This is called an ASCII Z string, and Z as in zero, the null byte at the end. And that indicates the end of a string. So the way strings work in C is they're just an array of characters where you put a bunch of character encodings in there, and you know you're at the end of the string when you bump into the 0 byte, the null at the end of it, right? ASCII Z strings. Questions about that? Other schemes for some other languages put strings in memory differently. You could put, like a Pascal string, the first byte would contain a number that told you how many things were in it. It doesn't have that walk across it till you hit the null concept, right? So there's different ways you can store strings. C does it with these ASCII Z strings, ASCII character codes, and then a null byte at the end. Okay. C, what would happen if you declared it char 5? Well, the basic approach in C is this language was invented for a couple of guys in a back room with a unused computer to hack the kernel of an operating system. And so the way they designed this language was assuming that the people that were using it were really, really knowledgeable about how it maps onto the computer. And there are no training wheels anywhere to be seen in this language. Programming in C is like walking around with a box full of hand grenades with the pins pulled on them, right? It's very, very, you can blow your toes off without even trying if you're not paying attention. And so anytime you have an array in C, he's never going to do anything that checks whether you're walking past the end of that array or not. It's like, I don't care if that's what you want to do it, right? So if you declared this to be 5 big and you put six things in it, it's just going to clobber whatever that next byte in memory happens to be, right? There are no training wheels in this language, right? All right. So let's start manipulating some bits. Boolean algebra. Way back in the 1800s, there was this Irish guy who was at the University of Ireland, which is in Cork in Ireland, and goes by, still goes by the name University of Ireland, but it's also called Cork University or University of Cork, whatever. And he came up with this thing called what we now call Boolean algebra. And it's called algebra because it behaves like the mathematical structure that we call an algebra. And the algebra that you've seen is the one that applies to numbers, right? But this is an algebra for dealing with logical entities, true and false, right? And so if we symbolize true as a one and false as a zero, talking about bits now, right? And then we can define some operations, logical operations, on those bits that are sort of the counterpart of the operations you'd have in your numerical algebra for addition and multiplication and all those kind of things, right? So the logical and operator, which is expressed in C with an ampersand, says that A and B is true when both of them were true, right? So the truth table, if you have these values for A and these values for B, then you get these results. If A was zero, false, and B was false, you get zero. So the only time the total result of A and B is true is when both of them were true, right? The vertical bar is the bitwise OR operator, and it's going to be true when either of the inputs was true. So you get this table, right? The only time it's false is when they were both false coming in. If either of them is true, you'd get a true as a result. The negation or the inversion of something is just the opposite of what you started out with. Zero turns into one turns into zero. And then this little guy here, the housetop, circumflex, whatever, is a exclusive OR operation. And what exclusive OR means is the same thing as OR, except not both. So if one or the other is true, but not both of them. So it only differs in this position in the corner here. One or the other is true, right? These two, but not both. So that's how he's different from OR, exclusive OR. So these are bit level logical operations, right? Well, then in 1937, along comes this guy named Claude Shannon, who's writing his master's thesis up at MIT, and he notices that we have these little devices called relays that are either in the open position or the closed position. And he noticed that, well, I can build a circuit that will behave like any logical expression. And so the way that this thing works is you got current coming in here, and then there you got current, and there you don't have current. So you have the opposite of whatever came in. And then you'd have this little relay thing sitting here, right? And the current would flow through there, and you'd say current shows up here exactly when this Boolean expression is true, right? Does that make sense? So that A and not B, right, shows up there. The opposite, not A, and the opposite, B, shows up here. So the OR of these two things is what the result of the whole thing is. And so he figured out you could take these relays and have this electronic circuit behave like any logical expression you wanted to dream up. Of course, nowadays we don't use relays for those. Relays are still around. You got relays in your washing machine and in your car. There's some relays that have to do with when it's starting the car and stuff. But um, for our logical stuff in the computers, we don't use those relays anymore. We use transistors, right? And we can do the same kind of trick here with our transistors and build any logical expression we want, and the circuit will behave like that logical expression. So if we look at back in memory, at things laying in the memory of the computer, we can apply bitwise logical operators to those bytes laying in the memory of the computer. So here's a byte, this value there, 8 bits is a byte, right? And we want to use the and, the logical, the bitwise and operation to and this other byte with this one. Well, you pairwise look at the corresponding bits, right? And the and says if both of them are one, then I get a one in the result. Here's both of them are one again. So I get all those zeros, and then only where the both of them are one do I get a one in the result. So bitwise anding these two things together gives me that. I could do my OR operation on it, and if either of them was a one, it shows up in the result. So the only place I get a zero is when they were both zero coming in. And my exclusive OR is one or the other of them was a one, but not both of them. So it's going to be the same as the previous one, except when both of them were one. So that zeroed out that one on the right there, right? Negation or inversion just flips the bits to whatever they were, right? So we have these operators in C, and we can do bit level operations on the stuff using the. Does that make sense? So then, why would we want to do that? Well, you could think of a collection of 8 bits as representing a set if you wanted to. And this would be the zero position. Is zero in the set? Is one in the set? Is two in the set? Is three in the set? So these ones in these positions would denote the set 0, 3, 5, and 6, right? And then this guy would denote the set 0, 2, 4, and 6. But if I took these two bit patterns and I ANDed these together, bit level AND, well, that would behave like set intersection. And I'd end up with 6 and 0 being in the set because they were both 1, right? The AND operation, if I'm interpreting that as a set, gives me intersection. Union is the OR operator. The symmetric difference, symmetric set difference, right, is the exclusive OR. And the complement of the set is just the negation. So I could use these operators on a byte, a couple of bytes of memory, if I wanted to interpret them as sets. But that's all in the mind of the beholder, right? The bit level operations are just doing their thing on the computer, right? However you want to interpret it as meaning a set is up to you. Does that make any sense? Okay. So this slide is screwed up. The little font messed up the characters there. So see if we can figure out what it should say. These operators and, or, not, exclusive or, apply to any integral type. Those are things like longs, ints, shorts, chars, unsigned, anything, any variables of any of those types. You could just take them and use these bit level operators on them, right? So, whoops, examples. What would be the negation of, and this means hex number, right? Hex number 41. Well, 41 looks like what? 4 bits with the 1, and then there's our 4, right? In the next 4 bits. Is everybody okay with that? And then I want to um, take B and E. So E is what? 14. So 14 in 4 bits would look like that, right? Oops. If I had all ones, it'd be 15. So putting a 0 there makes it 14, right? And so then this these 4 bits is my B, right? Is it 12, right? So I got an 8 plus no, it's an 11, right? B is 11 decimal. So I got 8 plus 4 plus 1 is 11, right? So there's my 2 hex digits in binary, right? And then I can apply some bit level operation, one of these guys, to that, right? Does that make sense? I'll go to the next slide. Now we have logical operators as well as bit level operators. So don't confuse the two. To get the logical operations, you write the bit level operation symbol down twice for and or, but then for the tilde, the dot, you write a bang, an exclamation point. So this is bang. So now what we're going to do is do logical, not bitwise operations. And the way the logical operations are going to work in C is you look at the contents of some variable, and if it's got a 1 in it somewhere in the bit pattern, we'll consider it as being true. If it's all zeros, we'll consider it as being false, right? The result of applying a logical operator is always the number 1 or the number 0, right? But the stuff that comes in, you view it as all zeros is false, anything other than all zeros is true, right? But it always produces the result of applying the operations, always produces exactly 0 or 1, right? Does that make sense? And once again, the slides are screwed up. But let's just pretend that we had um, some operator here and see what would happen. Hex 41, right? I get something up here we can use to do this. Oops, wrong command. Okay. So let's just screw around with this and see. Always use the computer to learn how to use the computer. So what if we had A is an int, and I want to put B as an int. And I want to put 0 in it. Looks a little silly writing hex 0 because it's the same thing as decimal 0, right? And now let's mess around with these things. Print F. If I could type, it would be great. Result is equal. And what do I want to do? I'll do like, let's try A and B. And before we do that, I'll do this. Okay, so we're going to print out A, but we got to tell him how to print it out. And so we want to see it in hex, right? So we got to put percent dot 2x. And we want to see the result in hex 2. Okay. And I got errors. Implicit declaration of function printf. Ah, classic. What did I do? I didn't include the header file. Pound include standard io.h. So now we got the thing compiled, right? Let's run it. Crap. Yeah, my fingers won't work. Okay, so what do we got here? We printed out A and B, and I screwed up somehow. I didn't get something done right. Percent 2x A. Huh. Percent dot 2x. What did I do wrong? Oh well. I'll work on it and show it to you tomorrow morning. Get some examples ginned up of playing with this. I got my printf screwed up somehow. Huh. Oh well. Anyway, I'm going to do my office hours again. Today they're 2 to 3 today. And so we can work on some more magic of the shell and magic of Emacs and show you some more goodies you can do with that. Or if you have any questions about the material, you can just ask me those questions. If not, we'll just do a little workshop type activity. So I'll either see you then or see you in the morning. I'm going to figure out how I screwed up the printf statement. See you tomorrow.